Swayam Prabha. Digital India. Educated India.
We have looked at different ways of calculating whether a project is viable, and mostly we've been looking at the economics as the basis. We've also seen how to look at the environment and environmental impacts and quantify that in economic terms. In this module and in the next module, we will be looking at how do we assess a project from an overall energy point of view. So first we will look at primary energy analysis. We have discussed this earlier in passing. Initially we talked about the energy flow diagram. That means we said that when we look at finally the energy that is required, we need an end use or an energy service. So for instance, if we are looking at illumination or the lighting that is being provided, or if you are talking about going in a vehicle, then we are looking at the distance traveled, we are looking at cooked food. That's the final energy service. And so this has finally the end use. For that we need some useful energy. That useful energy is coming in the form of we are getting some energy utilization equipment and systems. The energy that we are getting, the delivered energy the consumer is buying, that is also called final energy. So we looked at this final energy going to the useful energy. In order to supply the consumer, energy is coming through a transmission and distribution network. For instance, if you are looking at electricity, there is a large transmission distribution network which is coming in. That electricity is a secondary energy source. There is a power plant, there are coal mines, and finally we, from the energy service that we need and the useful energy that we use, we go backwards and we calculate the total primary energy or the energy that is available in nature. So we have already discussed this, but I'm just repeating. We have these different terms: the primary energy, the energy that is available in nature, that gets converted into a form like refined oil or electricity, secondary energy, that is then distributed and is delivered to the consumer. You get final energy. That final energy gives the useful energy, which is used for the end use activity to provide the energy service. So whenever we talk in terms of primary energy analysis, we will look at two different options in terms of draw the entire chain and calculate the primary energy which is required, and then with each step of this chain we can look at what are the efficiencies, we can also look at what are the emissions. So this is the primary energy analysis, where everything we convert and compare on the basis of primary energy. So as we saw earlier, with the different end uses that we can list down is, for instance, food cooked is the energy service, illumination for lighting, distance traveled for transport, shaft work for motive power, space cooled, fluid heated, and each of these have different devices like the chula, the stove for cooking, incandescent, fluorescent, compact fluorescent lamps for lighting, and for transport, cycles, cars, trains, motors for shaft work, fans, air conditioning, refrigeration, space cooling, boilers and geysers for heating. And in all of these there are many different possible devices, different sources, so we can have actually a whole set of different diagrams, the energy flow diagrams. So whenever we are looking at the types of decisions, we saw this earlier, where we are looking at either a yes-no kind of decision or a best possible decision amongst options. That is for system selection. We may also be choosing designing the system or the component For an existing system, we may decide an operating strategy and we may decide policies. And these are the types of decisions. And when we look at perspectives, we can look at it from the perspective of an end user, the manufacturer, utility, society, government, and others. When we are talking of primary energy analysis, we are looking at an option from the point of view of the entire chain, and that means we are looking at it from the societal point of view, the overall efficiency, the overall cost. We can also look at it from a subsection of it, that is from the point of view of the end user. And we will take a set of, for all of these decisions, there could be different kinds of costs, criteria. The cost criteria, we looked at initial operating life cycle cost, reliability, emissions, sustainability, and equity. In primary energy, we will be looking at the total amount of energy and the issues related to sustainability and emissions. So, in primary energy analysis, what we are doing is we are going to compare different options based on the primary energy input. For a given, we will decide a certain amount of final energy service or final output which is required, and for that we would compare these options, and then we will compare them based on the primary energy. We will draw the energy flow diagram or the energy chain for both or for each of these options, then compare, work backwards and compare the primary energy input. So let me give you a set of different examples and then we'll try and do a couple of them. So for instance, if you look at agriculture in all over the country where we are in our agricultural fields, we need water, and that water is pumped. So there are different ways in which we can provide the energy for the water pumping. The first one is we can have essentially grid electricity driving an electric motor. And the second option is that we can have a diesel engine running so grid electricity driving a motor, driving the pump, diesel engine directly coupled with the pump and driving the pump, so you don't need to actually generate electricity. We can have a gasifier running an engine and then running the pump, so there you have biomass, and then this could be a dual fuel engine, so there could be some amount of diesel. We can have solar PV doing the pumping. Okay, these are 4 of the options. We can have a whole set of other options also. We can have combinations, we can have hybrids. So we will look at this example. In the case of vehicles, let's look at, if you look at a car or a bus, and we can compare an IC engine vehicle. Again, this could be petrol, it could be diesel, it could be CNG. We will look at an example where we are comparing a diesel vehicle. We could have fuel cells and hydrogen. So that means hydrogen is the fuel. Hydrogen can be generated, can be stored. Hydrogen can come again from different sources. It could be from natural gas, it could be from renewable energy. We can have an electric vehicle running on grid electricity, and then you have the electric transmission, and then we can, so for all of these you will have a completely different chain, and we can look at the different primary energy use and the different emissions. We could also create biofuels from different kinds of biosources, could be waste, could be actually plantations, and then we can use these biofuels to run engines, and then you can have, so it becomes a renewable source. So this is in terms of cars and buses. Similarly, you can think in terms of cooking. For cooking, write down the different sets of options that we can have for cooking, and then for each of these again you can think in terms of making these calculations for primary energy. So let's look at now an option. We'll look at the first option, that is water pumping, and we want to compare the options based on primary energy input. And so the example is agricultural water pumping. If you look at, typically there are a large number of pumps used all over the country, and we have some measurements in terms of the kind of water used. The final end use which is there for the pump is the flow rate of water into the head that is developed, and that is the power output, which is the end use, and that multiplied by time depending on the number of hours of use. So based on the studies which have been done in the country, typically the value of end use which we require is given to us as 3 gigajoules. So we need, this is given 3 gigajoules of final useful energy, and we want to see what will be the primary energy requirement in 3 cases. You could also do a similar thing for solar. We are not doing that in this. The first one is electric motor pump. The second, B, is diesel engine pump, and C is the biomass gasifier dual fuel engine pump. So if we look at the electric motor pump, just take a minute and sketch the diagram, schematic diagram of the energy chain. So we will start with, basically we will have the pump, then before that will be the electric motor, this is the useful energy output, which we are given as 3 gigajoules per year. Now this is the electricity that is purchased by the farmer, and if you look at this boundary, this system boundary is what the farmer sees. So here, if you look at this as eta motor and eta pump, the overall efficiency which the farmer sees is eta motor into eta pump, and so the energy input required in terms of electricity input is 3 into 10 raised to 9 joules divided by eta motor into eta pump. Now here, before this, you would have that electricity that we are getting is coming through a transmission and distribution network. So you have a transmission and distribution network. And this will also have another efficiency, eta T and D. This is the secondary energy that we are getting, and before this we have, you would have the power plant, eta power plant. Before the power plant would be the, if we think in terms of coal, you would have the coal mining and transport, and then this is your primary energy source, which is coal. Of course, you could have the similar thing from hydro or from any other source, and so here again you will have eta Cm, right. So if we look at this overall efficiency, this is going to be eta Cm into eta Pp into eta Tnd into eta M into eta P. That's the overall efficiency. So this is what we have just now seen. If you see it now in the better fashion which we have seen, this is the values. Now we can put down typical values of this. Even if we look at the best values that we have for motors and pumps, we can put down these values and you can calculate these. Now, just to give you an idea, you may want to think about how you would calculate these. For instance, if we want to see how to get the efficiency for coal mining, we would look at a particular mine and see that in that mine, how much energy is being used, electricity as well as diesel, convert that in terms of energy terms, convert that in terms of the kgs of coal which is being mined, and then see what is the output and what is the input. And based on that, we can get an efficiency. In the case of transport, if we see, if the coal is being transported by train, we would look at the distance which is being transported. For that distance, then we would see how much is the, if let's say it's an electric train or it's a diesel, how much energy is being used, and see the total carrying capacity, divide by that, and we can get what is the energy used per kg of coal, and then convert it all in terms of percentages and get an efficiency. These are not very low. There's not too much of energy is used in the transport or in the mining, so the efficiencies are relatively high. However, in the power plant, that's the point where we have the loss of the efficiency, because we have basically the understanding that when we are talking of transfer of heat to power, we have the thermodynamic limitation, and that's why you will find that power plants typically will have slightly lower efficiencies, and that is the power plant and T&D. So if we look at, these are the typical values. You can cross check these, but these are the typical values that we see. Motors, the good efficient motors will have 88%, and pumps, if rated as its best efficiency point, maybe 75%. In actual practice, pump may be operating at part load, and the motor may also be operating at part load. So you may find that instead of 88 and 75, we may be looking at something like 50% for the pump and maybe 60%. So then that becomes, the overall thing becomes much lower. So let's look at what is the efficiency that the farmer sees. In the farmer side, we are looking at an efficiency of eta motor into eta pump, which is 0.88 into 0.75, right? 3 by 4, so 0.22, this is comes to 0.66, 66% efficiency, right? And we also said that, let us say 3 gigajoules of electricity which is being used. So that means this is 3 gigajoules. The input energy will be 3 into 10 raised to 9 divided by 0.66, right? So if you look at this, we will get this as the total amount of energy which is being used. You can just check this 3 divided by 0.66, it will be approximately, we can just check this, 3 divided by 0.66, it's 4.54. Now, if we want to convert this into the amount of electricity, you will find that this is 4.54 into 10 raised to 6 kilojoules. 1 kilowatt hour is 3600 kilojoules. So if you do this, you will find that this comes out to be something like 1263 kilowatt hour. Okay, so we found how much is the energy which is being used at the site. We can also calculate the overall efficiency, and the overall efficiency will be eta overall for case A is eta Cm into eta Pp into eta Tnd into eta M into eta P, and this is 0.9 into 0.3 into 0.78 into 0.88 into 0.75. And if you check this, this comes out to be 13.9%. So we saw that from the point of view of the end user, we are looking at this as 66% is the overall efficiency at the farmer site. But if you look in terms of primary energy, this is going to be 0.139, and we can also then see how much is the input primary energy required. Primary energy input, this is going to be 3 gigajoules divided by 0.139, and you can calculate this as 21.58 gigajoules. We can also convert this into the amount of coal that is being used. So suppose we are looking at this as, let's say, coal has a calorific value of 5000 kilocalories per kg, then this will be 21.58 into 10 raised to 6 kilojoules by 5000 into 4.18, right? This is kilojoules per kg, this was in kilojoules, so this will be in kgs, and you can calculate, it will give you approximately 1300 kgs of coal. You have calculated now what is the primary energy that is required. So in a similar fashion, let us look at now the second option. Second option is where we are using a diesel engine. So even a diesel engine, if you see, we start with, if you look at this again, you will have the pump, and then before the pump, instead of an electric motor, you just have the diesel engine. Then the diesel which is coming to the farmer, then we have, this is the final energy, this is 3 gigajoules, and this is the diesel which is being bought. This is our farmer's boundary. We will look at this as eta pump, eta diesel engine, and then there will be the diesel which is being transported. There is something similar to our diesel transport, TND. This is like the TND, right? TND. And then we have the refinery, and then we have the maybe the oil well, oil extraction, and then this is the primary energy, which is crude oil. We have taken this together as one term with eta r as the efficiency. This we are talking of is eta dt. So if you see it now here, the same thing which we've drawn, crude oil, and we have merged the oil extraction and the refinery into eta r, diesel transport eta dt, diesel to the farmer, diesel engine, and then the pump. So now let us calculate for the farmer's site now, the efficiency that the farmer sees is eta d into eta p, which is 0.4, 40%, 0.75. So the farmer, at the farmer side, the efficiency is 30%. And if you look back at what we calculated earlier for the farmer in case A, the farmer's efficiency was 66%. So from the point of view of at the farmer side, the farmer sees in case A, efficiency is 66%. In the case of B, it is 30%. So it looks like the diesel engine pump efficiency is half the efficiency of the electric motor pump, right? So that's an interesting thing to see. So it looks like it's less efficient. Let us look at it in terms of, so that means the input energy that we now need, input energy will be 3 gigajoules divided by 0.3, which is 10 gigajoules of input energy, right? Let's look at now the overall efficiency. Overall efficiency, if you see, refinery is 0.92, diesel transport is 0.95. So the overall efficiency is going to be eta r into eta dt into eta d into eta p. 0.92 into 0.95 into 0.4 into 0.75. So that comes out to be 0.262, 26.2%. So now if we compare that with what we had calculated for case A, you will find that in the case of for case A, we had calculated this as, let us see, 13.9%. So we see that case A, case B, from the farmer side, at the farmer end, if you see the efficiency, for case A, it was 66%, case B is 30%, and overall this is 13.9%, 26.2%. Interestingly, what you find is that it gets almost reversed. So here it is, in the case of B, this is in the case of the farmer, for A it is double that of B, and that means the electric motor pump seems to be more efficient than the diesel engine pump. But from an overall, so when you see the entire chain, this is 13.9, which is almost, it's a little more than half of the case B. So B looks more efficient from an overall point of view, but at the farmer end it does not look so efficient. And so that's an interesting point. We can also now calculate, like we calculated the amount of coal which is being used, we can also calculate the amount of oil, crude oil which is being used, or the amount of diesel input. So the amount of diesel input which is there will be just 10 gigajoules divided by, let's say, 9,700 kilocalories per kg into 4.18, and we want it in liters because that's the unit which we see. So it's 290 liters of diesel. So now we can see, we can calculate how much here we are buying 1263 kilowatt hour. From the farmer point of view, what is the difference in the operating cost? If you look at that, we can just take, let us say, of course, earlier people, we used to have subsidized electricity, and now let's say we are paying 3 rupees per kilowatt hour, then this will come to about 3789 is the annual cost of operation. Motor pump, relatively the capital cost is only, you are only paying for the motor pump, so capital cost is of the order of 12,000 rupees. In this case, the operating cost is 50 into the 290, and this comes out to be 14,500 rupees. So obviously the diesel engine pump, the operating cost is higher than the electricity cost. The capital cost is also higher because for the diesel engine the cost is there. So from a cost point of view, this is the diesel engine pump set looks to be a costlier option. From the farmer point of view, it looks like this is a cheaper option. Also, this is a more efficient option from a farmer point of view. Capital cost is also lower, operating cost is also lower. The disadvantage is that in most of the country, of course, the situation is improving now, but a large amount of, for the agricultural pump sets, there are a number of power cuts, and so at the time when you want to use it, we may not be able to get the. So then, and in this case, this is uninterrupted. You can use it as per requirement. We calculated 1300 kgs of coal, and similarly we can take the oil and then divide by the calorific value of the crude, and you will get this as 300 kgs of crude oil. You can cross check this. Now the question is, how do we compare 1300 kgs of coal with 300 kgs of crude oil? From an energy viewpoint, this 300 kgs of crude oil is less energy. However, we have, from a national viewpoint, coal is relatively abundant, and also in this case we can change the mix. As the mix changes, there is a flexibility, so it need not necessarily be on coal, it could be on oil, it could be on gas, it could be from renewables, while here it is definitely on oil. And then there is an issue in terms of the refinery mix. So as we have seen earlier, in India we have the largest chunk of our requirement for oil is coming through imports, but we have a lot of refining capacity. So there is a lot, mostly we are refining crude, and when we refine crude, we get the heavy fractions, the middle fractions and the light fractions. In the middle fractions, we have kerosene and diesel, and what happens is that the requirement for diesel is high. So when we have a particular refinery mix, you will get, for a particular amount of crude, you will get a fraction, some percentage which will come in the middle distillates. Now that percentage is not sufficient for the requirement that we have, and we are also importing the diesel and kerosene, and with the result that we have what is known as a middle distillate bulge. And so from a refinery mix point of view, you would like to see if we can reduce the amount of diesel consumption. So this shows us from different perspectives how primary energy analysis can be used to make the calculations. We will also, the one last thing that we would like to see on this example is that what about the CO2? So we can take the, suppose we are saying 1300 kgs of coal which we are using, we can take this as, let's say, 54% carbon into 44 by 12. This will give us annually the total amount of CO2 in option A. So these are simple calculations which we should be able to do, and this will result in, this number comes to 702 kgs of carbon, multiply by 44 by 12, this will be 2574 kgs of CO2 per year. That means one agricultural pump has 2.5 tons or 2.57, 2.6 you can say, 2.6 tons of CO2 per year is the emission. If we look at this now from the point of view of the option B, which is the diesel engine, we can then now see that this is going to be a 300 kgs of crude oil, let's say approximately 0.84. This comes to 252 into 44 by 12, 924 kgs of CO2 per year. So this is also something that helps, that the primary energy analysis helps you do. It tells you about the overall thing. And so this comes out to be 0.9 tons of CO2 per year. So from a CO2 viewpoint, it's better to go in for diesel, and then you see the trade-offs. Diesel is costlier. From a societal viewpoint, there are issues in terms of imports and energy security. From the option of CO2, the oil option is better. From a security option, the coal option is better. So these are the kind of trade-offs which are actually there in many of the cases.